Welcome everyone, my name is Melanie Turquie and I'm a junior at Louisiana Tech University. My research focuses on the direct detection of overexpressed microRNA associated with thoracic aortic aneurysms using magnetically amplified hairpin molecular beacons. Thoracic aortic aneurysms affect approximately 15,000 people in the U.S. due to multiple factors such as hypertension, substance abuse, connective tissue disorders, family history, and vascular inflammation. These diseases' symptoms are silent and go undetected unless there's an off chance that it gets caught in image screenings. With these statistics, underserved populations are even less likely to detect this disease. To combat these costly challenges, a nucleic acid test is used to detect the microRNA strand that is associated with TAA by utilizing surface-enhanced Raman spectroscopy, which is also known as SARS. The use of metallic nanoparticles in addition to these biomarkers can be used to enhance the Raman signal, which will cause detection to be more easily achieved. The start of the research began with detecting probes by attaching them to silver nanoparticles in order to obtain a quantitative measurement of SARS signal. The intended goal is to obtain characteristic SARS signal of TAMRA tethered to nucleic acid capture probes so that it can be implemented into AIM2, which consists of synthesized magnetic particles coated in silver nanoparticles, to allow for the same microRNA probe detection with addition of magnetic separation. AIM3 consists of target capture of microRNA for a quantitative measurement by collecting SARS measurements of microRNA capture. The intended goal is to see a decrease in SARS signal at distinct TAMRA characteristic peaks. The end result should include molecules attached to silver nanoparticles in a hairpin structure which will exhibit SARS on and SARS off for each given state. The methods used to approach these aims consist of various procedures to test for SARS signal and optimize parameters in order to receive maximum readings. Silver nanoparticles were modified to have a wavelength of 435 nanometers and 1.76 absorption level, and we experimented with 0.5 micromolar, 1 micromolar, and 2.5 micromolar probes in various conditions. It was found that heating the probes for 20 minutes at 90 degrees Celsius produced the optimal signal after 24 hours of incubation to allow for probe attachment. This process is then integrated with the attachment of magnetic particles by incubating 300 microliters of silver nanoparticles and 50 microliters of magnetic particles for 30 minutes to allow for core satellite attachment. From there, 50 microliters of heated probes were added and incubated overnight in order to attach to the surface. These results from AIM1 show the distinctive TAMRA peaks that correlate with the detection of probes. Because the hairpin loop is closed, the TAMRA dyes tethered to the oligonucleotide probes are close to the nanoparticle surface, giving us massive SARS enhancement. The 0.5 micromolar probes gave us the best signal for the TAMRA peaks. Figure 3A shows a TEM image of the magnetic nanoparticles synthesized. We have used a hydrothermal method to synthesize these particles. This was achieved by mixing iron chloride, sodium acetate, ethylene glycol to form a homogeneous mixture. Under high pressure and temperature of 200 degrees Celsius for 8 hours, magnetic nanoparticles were synthesized, with an average diameter of 92 nanometers and a standard deviation of 13 nanometers shown in Figure 3B. To continue the goal of AIM2, silver particles were then attached to magnetic nanoparticle cores. To optimize this process, we first evaluated the surface charge of magnetic and silver nanoparticle surfaces. Figure 4A represents the data we have collected. It was seen that the magnetic nanoparticles have a positive charge, while silver nanoparticle surfaces have a negative charge. We use this charge difference to allow for electrostatic interaction between the two nanoparticles by mixing it together with various loadings. You can see that from our first loading, the innately positive charge of the magnetic nanoparticle core becomes slightly negative, and after the second loading, it becomes more negative, from 13 millivolts to negative 32 millivolts. A similar study was conducted with UV-Vis. We have seen continually broadening as we attach the silver nanoparticles in the magnetic nanoparticle core surface. In conclusion, we can note the uses of nanoparticles paired with biomarkers does enhance its Raman signal, which can further be beneficial to further detect silent diseases. Adding magnetic nanoparticles allows for separation without centrifugation machinery, making the process lower in cost and more accessible. Future directions of the research would be to complete AIM3 by optimizing the target capture probes to control the SARS on and off signals, and implementing these results into a device that can be used at the point of care setting. That concludes this presentation, and I thank you all for watching.